Raise your hand if you're here to learn about servers. Are you sure? Servers? Okay, just kidding. We're going to be talking about serverless today, and thanks for joining me here. There's tons of sessions here. I hope you've had an awesome re:Invent, but I appreciate you joining me here for the next hour. My name is George, and I'm a senior distinguished engineer with Capital One, and I'm responsible for leading our serverless center of excellence. And I'm mostly spend my days helping our company become more cloud native and then drive towards a serverless-first compute architecture across Capital One. Before my time at Capital One, I spent almost 7 years at AWS, where I was the tech leader for serverless compute, and I had the opportunity to work with tons of customers all over the place, building really cool applications on Lambda and all of the services that you might be using today. So who here is building an app on Lambda today? Cool, it's like half of the room, awesome. How about who is exclusively on serverless Lambda today? Maybe like 10%? Okay, cool. So this is kind of going to be, if you're based in the US, I think you probably know who we are as a bank, but we're actually one of the top 10 banks in the US. But if you're not from the US, you might not be familiar with Capital One. But we are essentially, everything we do is rooted in technology. So you might have heard in 2020, we closed our last data center, and we moved all into the cloud, and we operate everything kind of like a tech company. So most people don't know that, but we are all in on AWS. And this, in 2020, we were really successful in doing this. Today, we're kind of on a different journey. We're no longer migrating to the cloud. We're now building cloud-native, serverless compute architectures. So this is just kind of a little trajectory of where we're headed and where we started. What's really cool is last year we began to become a platform company. So many of you might be using like Snowflake. So we started building software to manage your Snowflake deployments and configurations. So that's going to be our trajectory for the next many years. But let's get started. So this session is going to be kind of an intermediate session. We'll be talk a little bit technical. We'll start with why Capital One, decided to adopt a serverless-first approach. And then we'll talk about some of the lessons that we learned. Hopefully, you will be able to take away those lessons so that you don't make the same mistakes that maybe we made. And then I'll talk a little bit about how and why we created a center of excellence and how that helps us drive towards serverless maturity. We'll close, and I'll leave you with a bunch of best practices that you can bring back to your organizations for building in serverless apps. OK, so why did Capital One adopt a serverless-first approach? So to answer that, we have to look at this diagram. I think everybody's familiar with this. This is the gold standard for how AWS wants you to deploy highly available and resilient applications in the cloud, right? Everything fails all the time. So you have, in a single region, you're going to deploy applications across multiple availability zones. Each availability zone will have auto-scaled EC2 clusters, and then you load balance across those regions, or those AZs. And the reason you do this is because everything fails, and if something fails in a data center, we can recover and load balance across other areas. So in the pre-serverless world, the span of control that we had to do kind of looked like this, right? You operate on the cloud, and when you operate on the cloud, you have to, most of us are probably not writing directly in the console, right? We're probably automating using some kind of deployment tool. But next step you have to do is, when you're in the server full world, I guess, is you typically deploy EC2 instances, which means you have to manage the AMI that goes on that instance, the Amazon Machine Image, the networking, all the stuff, the scaling, and the auto-scaling groups, and everything that load balances onto those instances. So at this point, we haven't even begun to touch or create our applications, right? And then you configure the operating systems. Most of us are probably deploying to Linux or a Unix-based operating system. You have to patch it, operate it, decide what version to use, upgrade it, So tons of work, right? And then I think most of us these days are then deploying containers on top of our OSs so that we can have portable environments. And then finally, we put our app servers on them so that they can service whatever workload we're trying to build. And finally, this is where our developers really begin to build applications. Right? They start to build the apps that are unique for your business. I spent probably 10 years as a full-time application developer, and I think all of us used to build applications just like this. Right? You have these gigantic, anybody remember these gigantic ear files or war files that you would create in Java and deploy them onto really big app servers? And then how do you scale that? You just add more app servers, right? So everything at the bottom down there is what we call run the engine. So it's stuff that doesn't really add any value to your apps, but you have to do anyways, right, in order to even get to the top level business app section. And developers are skilled at writing code and delivering awesome features. Right? They're not skilled at all that stuff down below. If you hear AWS talk about this, they call this undifferentiated heavy lifting, or sometimes Capital One calls this arbitrary uniqueness. Right? So when you move into the serverless world, usually your applications become event-based or event-driven instead of, in the previous world, you just have a cluster of servers waiting for work. And those servers might expand and shrink, but at the end of the day, it's a bunch of servers waiting for work to arrive. And most enterprises are probably utilizing those servers at about 30 to 50% utilization. So there's a lot of waste, right? So in the serverless world, an architecture usually has 3 ways of being invoked or driven or run. First is synchronous, and this is really easy to understand, right? It's just an event arrives, and we have to invoke a function to perform some kind of work. And the best example of that is an API. You might be building an API that services your customers, whatever feature you have, and you have API gateway that is performing the load balancing, authorization, and then invoking your Lambda function. So in this example, an order just arrived, and it delivers the metadata and events to your Lambda function. The second way is asynchronous, and this is actually the best way to operate. So asynchronous is, if you went to any of the keynotes a couple days ago, you'll notice a lot of focus on all of the event sources that invoke Lambda, or Kinesis, SQS, all of those SNS, right, S3. It's an event happens, something happens in your ecosystem, and you have to respond to it. So a really great example is, all of us are probably on some form of social media today, and we're always taking pictures, hundreds of thousands of photos on our phones. Those social media providers are not simply just taking those pictures that you took and then uploading it to the internet, right? They're storing those images, and they have to do something with those images. They're mostly doing resizing, optimization for the web, creating different sizes of images that are suitable for laptops, mobile devices, big screens, and then they're delivering it out to us to consume. So that's an example of an asynchronous response to something that has happened in your ecosystem. And then the last way is pull-based. So Lambda has created an amazing feature that they don't really publish information about, and it's actually called, basically, it's a poller that will poll any one of these event sources on your behalf. So if you're pushing thousands of messages into Kinesis, into Dynamo, or into SQS, right? If you're running on traditional architectures, you have to write code to pull and get those messages out. And that's a lot of work. You have to scale that polling mechanism, and you have to make sure it doesn't have any bugs. But if you're running on Lambda, AWS does all of that for you. So take advantage of the poller. It's completely free, and it doesn't cost us anything, right? And then basically any of those messages that arrive, there's different mechanisms and why you would choose specific services, like if you need ordering or payload size. But at the end of the day, Amazon will grab those messages out, deliver them to your function, and then invoke those functions as messages arrive. So a good example is you might be creating an order system, and you don't want to have your order system coupled with your payment processing system, right? So you have messages arrive, your processing system could be entirely off, right? But you're still able to take orders, right? And when you turn on the processing system, that's when your whole system activates. All right, so in a serverless world, remember the example that we looked at earlier, everything at the bottom is just basically just in the cloud. And that's what we really love about serverless. So when you're in the cloud, the first thing you have to do is choose whether you want to do your serverless compute on Lambda, which is functions, or Fargate, which is serverless containers. Right? You can do Fargate, standard Fargate, or you can do EKS on Fargate, depending on your requirements. And then your developers write business logic directly in those functions. And the first thing your developers have to do is really write business logic, and there's nothing else they have to do on the bottom there. So AWS manages everything at the bottom. We love that feature, basically, and the developers love it too, because they don't have to worry about any of those networking, patching, rehydration, anything that has to go on behind the scenes to even operate your AWS fleet. And developers can focus on delivering applications that matter to your business. All right, so in a quick summary, we love serverless because it means happy developers. And our developers are 100% focused on writing awesome code. Obviously, there's still vulnerabilities that they have to address if they use libraries that have vulnerabilities, but basically infrastructure vulnerabilities go to zero. And then our business is happy too, because for the most part, your AWS infrastructure cost will drop drastically. Right? You don't have these clusters of servers waiting for work. Right? You have event-based applications that only run when there is work to be done. And that's a really powerful change in the way we build applications. And then the last thing, I think you'll hear this theme a lot, is modern apps. That just means that today we're building a lot of different microservices that can scale independently. And that's super important because you might have multiple components in your system. Not every one needs to scale together. Right? And that is what serverless allows us to do. All right, so let's go to chapter 2, which is where we talk about some of the lessons that we learned and help you speed up your serverless development. So Capital One runs, we're all in the cloud, so we run thousands of accounts. And we have so many accounts, and in those accounts, we have tens of thousands of Lambda functions. So what that means is there is no way I can go anywhere and manage these accounts or Lambda functions manually. And these are all challenges on the bottom that we have to deal with. So Capital One we're in a regulated industry, right? So we have compliance that we must hit, and it's not optional. So we have to create controls around how we operate these accounts. There's things that we can and can't do. So IAM is the gate for permissions. So we have to manage IAM very, very tightly. We create standards. So these thousands of Lambda functions, if you don't create standards, you'll never be able to manage these things. And I'll talk a little bit about some examples that we have settled on that have helped us manage these functions. And then metrics and logs. What do you do with, when you run a Lambda function, it generates tons of logs. Those logs cost money. Right? CloudWatch logs are not free, unfortunately. And then you have to maintain this whole fleet. Right? There's vulnerabilities every day. I bet right now there's some 10 vulnerabilities that just got released. Does anybody remember maybe a few years, maybe like 4 or 5 years ago, there was this Intel vulnerability, Spectre and Meltdown? If you were running on EC2, you probably got paged, emailed, called, whatever it was, to go and patch your EC2 fleet. Right? Running on, and I was still at AWS at this time, but running on Lambda, which basically meant you just watched Twitter. Right? There's nothing for you to do. AWS handled all of the hard work to patch and deal with those vulnerabilities. And that's super important for us because that gets our developers away from all of that hard work, like infrastructure management. So in order to make this happen, we learned that we needed to create a centralized center of excellence. So early in our days, we were making decisions that were isolated by one team that would affect the whole enterprise. And we have 10,000 engineers, right, across multiple lines of businesses. So I work for our retail line of business, which creates all of the software that you might use as a customer that, to interact with the bank, right? The mobile app, the website, cafes. There's a credit card line of business, which manages the credit card that you might use to pay for your hotel here. But there's tons of other lines of businesses, including enterprise, risk, and security. Early in our days, we made a decision in one point, in one LOB, in a line of business, and we didn't really engage other lines of businesses, and we didn't really have an idea of how these decisions would impact the enterprise. So I guess on the right there, you can see the main purpose of our COE is focused on serverless, but it helps set standards for how our engineers deploy Lambda functions, and we roll out a lot of enablement activities. So one thing I'll talk about a little bit later is the shift in mentality and the education that you're going to need to go through to shift your organization to a serverless-first mindset, right? And then, so we provide subject matter expertise to the company as well. We have deep technical experts in the COE that help unblock our engineers. Serverless is, getting into AWS is the base foundation, but then you have to learn serverless, and it's going to be new to everybody. And the main thing is avoiding tech debt. So you have to have a COE to help avoid tech debt. So this is kind of how we operate our COE. It's basically led by an accountable executive, which is one of our VPs, and then a lead distinguished engineer. So together, these two roles work with representatives from every line of business, and we meet on a monthly basis to talk about all kinds of ongoing enterprise issues. So one example would be, if you're working in Lambda, AWS routinely deprecates the runtimes, right? So node 12, node 14, 16, 18, AWS eventually will say you cannot update those functions, and then you cannot even create functions in those versions, right? So what do you do as an organization when that happens? And so this is stuff that we talk about on how we want to manage our upgrades for runtimes. And so there's 6 or 7 supported runtimes for Lambda, right? There's Go, Python, Node, Java, .NET, and am I missing anything? There's a custom runtime as well. But so imagine you have to manage upgrades and deprecations for 5 or 6 different runtimes across millions of Lambda functions. All right, so our COE is driven mostly, we use Jira ticketing, so we assign tickets out to workstream owners who help us address these issues. We create documents that basically end up becoming enterprise-wide guidance on how engineers should do things. Another example is we have a library that is being deprecated internally for managing our secrets, and so it's important to be able to have an enterprise-wide strategy on how that happens. So some other sample things our COE leads are like, Lambda has all these default settings, right? And so by default, there's no reserved concurrency for Lambda. And we have to think through, do you want to have reserved concurrency or not? Right? So setting reserved concurrency means you can only run a certain amount of Lambda at any given time for that function. If you set reserved concurrency on every function, that means every function you deploy is consuming available account concurrency. It's kind of like when when COVID first started, everybody went and ran out and bought toilet paper, right? Even though you didn't really need it, right? And then there was none available anywhere, right? So if you set reserved concurrency on all of your accounts by default, that's the exact same thing that's going to happen. Everything consumes concurrency, and then eventually, when you do need to scale, you're not able to in your accounts. So like the COE has to think through stuff like that. Naming conventions. When you deploy more than one Lambda function, you should probably standardize on how you name these things, because as you get bigger, if if you don't have naming conventions, it's going to be really tough to understand what this function does. You can name a function blah, 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 George, right? And that doesn't mean anything. And then memory and timeout, right? Memory and timeout are the two factors that that AWS uses to price your function, right? So memory, does anybody know, for memory, does AWS bill us? Raise your hand on memory. It's memory consumed and memory configured. Raise your hand if it's memory consumed. Nobody thinks it's consumed? OK, that's amazing. It's memory configured on your function, right? So if you configure your function to run at a gig of memory, and you only use 128, AWS doesn't care. They're going to bill you at a gig, right? So the COE needs to help write guidance on how we should optimize for cost efficiency. And timeout is similar, right? Lambda functions can run for 15 minutes. And the longer you run, the more it's going to cost us. But that doesn't mean you should run a function for 15 minutes just because you can. We talked about the runtime deprecation process. Those languages are the 3 most popular runtimes in use at Capital One. I think that's mostly true across the world for the most part, from my experience. Node and Python, they're interpreted languages. They cold start very quickly. Java is just everywhere. Like every enterprise has Java. A lot of us are using Java 8. We need to get out of Java 8. Just by default, moving Java 8 to 17 delivers about 20% performance improvement. So simply just getting out of the old legacy Java will help you a lot, right? So on the right there, our COE creates monthly, weekly training initiatives for all of our associates across Capital One. And then we run a biannual, semi-annual tech summit that deep dives into topics that we're just about to jump into. So we learned that as we move across this journey, there's going to be a learning curve for all of your developers. So the beginner serverless developer always writes functions in the console. And when Lambda first launched, does anybody remember back in 2015, the only way to create a Lambda function was basically in the console. Right? You go in the console and you write this code. And when you have problems with that code, what do you do with it? Like normally, not even using Lambda. Right? When you have problems with code, you debug it. Right? You put breakpoints in your IDE, you run the debugger, and then you can step through and watch all of the variables. And then you can quickly find the issue. Now, the problem with Lambda is you can't do that. There's no way for you to attach a debugger to AWS. You can't put a breakpoint in the cloud. So the beginner engineer usually ends up writing a bunch of console log statements to output variable names and variable values. And that's really the only way you can do it. So you can't debug a Lambda function, and you can't really trace through it. So it's very tough for engineers to debug complex issues. Memory leaks are really tough to do. So what do we do? Like this was a big challenge for us. We don't want engineers to do this, right? We want engineers to be productive and iterate quickly. So there's something you might have heard of. It's a tool called SAM, and SAM stands for the Serverless Application Model. And if you see that little squirrel anywhere, it's basically the SAM mascot. Don't know why they chose a squirrel, but SAM provides 2 interfaces that are super important. One is the SAM CLI. You install that locally on your machine, and then what comes with it is a Docker image. Right? So there's a Docker image for every single runtime that Lambda supports, and AWS manages all of this. So what that allows you to do is create a Lambda function locally, and then execute that function locally, and then emulate what it would look like in AWS. And the goal is to be able to write all your Lambda functions locally, iterate until it works, before you go into step 2, which is using the CI/CD features of SAM to deploy into AWS. Right? And this is extremely powerful because it saves tons of time and allows your engineers to do what they're used to doing, which is local debugging in their local environments. This is a shorthand example of a shorthand syntax. So when you're using SAM, you're going to have to write a CloudFormation template that's going to be an abstraction of the massive amount of stuff that CloudFormation supports, right? So has anybody written a CloudFormation template? Like, they can be 30 pages long, right? They can be gigantic. So, but when we're working as serverless, most of us are only using a small subset of the AWS services. So what SAM does is it only supports like 8 or 9 different resources. And then on the second line of any SAM template, you'll see the transform directive. It'll say AWS : serverless. And then right now, there's only one version of it. There may be more in the future. I don't know. But when AWS sees that transform directive and you deploy this function, it's going to convert this SAM template into a real CloudFormation template behind the scenes. Like, you don't have to do any of this. First thing AWS does is it reads it in, and then they will convert this to CFT, and then they will write out the real CloudFormation template. But this example deploys two Lambda functions. You can see it's a SAM template because everything is namespaced with AWS serverless. The first is called foo function. Second is called bar. They're using Node.js 16, and then their memory size 128. So let me jump into a SAM. I'll give you a real quick demo of SAM, and I'll show you how most engineers use SAM. So this is a very simple demo, right? It's a very basic SAM template. If you can see here, there's a file on the left called samconfig.toml. Right? So when you're working with SAM, it's all CLI based. So all of your commands will be really long. They're going to be SAM local, invoke, function, and then you give it a whole bunch of parameters. So our first tip is always create a SAM toml file where you can default all of your settings, right? Invoke images, everything that you might need to run your function locally all goes into this file. AWS has this documentation on their website. You can check out all of the supported features and flags in this file. But what we want to look at is the template YAML file. So as we just saw on line 2, there is a transform directive. Yep. And then, so see this transform directive? This tells me this is a SAM template. It supports something called globals, which is if I know that I have common settings for all of my resources, I can define it in one place, and SAM will automatically set that on all of my resources available. But the most important piece of this is the resources section. So this is where you configure all the resources that you want to deploy. And then we can see I'm creating a serverless Lambda function right here on line 13. And then it uses the node runtime. I'm using 256 memory. And I'm setting a bunch of environment variables. So the handler setting is the most important piece here. Right? This says, where do I want my execution to begin for Lambda? And in this case, it's a file named handler and a function called handler. Right? You can call this anything you want. So that means on the left here, I have a file named handler. And then my function entry point is also called handler. Right, so it's super easy to understand. If you're reading any SAM template, you'll be able to jump into here really quickly. So this doesn't really do much. It just ingests an SQS event that came in, and then it'll process and respond. So with SAM, on the bottom here, I have a terminal. So if you type SAM local, and this is just the namespacing for how AWS wants you to use SAM, if you do invoke, and you hit enter, by default, it's going to invoke the first available Lambda function in your SAM template. And let me, I usually like to use this little plugin called JQ so that you can have syntax highlighting on your stuff. All right, so as you can see here, every Lambda function, when Lambda functions log, they always have a start line. And the start line always has a request ID. And this is really important because anytime you open a support case with Amazon, the first thing they're going to ask for is what is your Lambda request ID? And because they use that in order to trace what happened on the back end. Everything after the start line is going to be Lambda logs, right? Logs that your function wrote, right? Logs that we consoled out. And then there's going to be an end line. So the end line is the same as the start line. It just closes the execution of that Lambda function. But the most important piece of any log is the report line. And so we'll talk about that in a little bit, but you'll notice every report line has certain fields on it, like the initialization duration, the execution duration, this was 109 milliseconds, and then the build duration. So we can see here, execution was 109.4, build was 110. So AWS builds Lambda at a granularity of 1 millisecond. So it's the most granular service that AWS offers. Nothing else builds at that granularity. And it's super awesome because that really represents the work that's being done by this function. And then one thing you'll notice when you're using SAM here, remember we talked about memory configuration. So again, you're billed at the amount of memory you configure for your function. When you're running locally in SAM, these are always going to equal. Right? Just that always confuses engineers to begin with. The memory size is what you configured it at. The max memory used is what your function used. If this was running in AWS, it would represent a real number. Right? But locally, it's always going to equal. So you don't really want to do performance testing locally. You just want to do feature testing and unit testing locally. Right? And then down here is just the response body. Right? This is I have a hard-coded response for returning I think this is a required body for an ALB response. Right? And that's it. So, but there's a couple other cool things. SAM local can generate events. SAM local generate event. So you can see, if you're ever confused about what does an event look like when it comes from a certain service, for example, if we look here, there's tons of services listed here. The third one is ALB, right? So if you need to know how AWS generates an ALB event, you can just come to SAM and do SAM local generate event ALB. It'll give you a sample output of what an ALB event looks like. So if we do this, ALB, it's going to say some services allow different types of events, right? So in this case, we have an event for ALB requests. And so you get a JSON log. Here, let me make this a little prettier. GQ. And basically, you get a little output that shows you what a schema for an ALB request looks like. Right? So if you're not even doing serverless development, SAM's a cool way to just come in here and learn what events look like for certain services. And there's like 20 of them in the list or something. OK, cool. So let's go to the next slide. I highly encourage you to use SAM as your default way of working with Lambda. I think it's super powerful. What comes after that is the deployment and CI/CD mechanisms. We don't use that at Capital One, so we actually control how deployments go out. We have a pipeline, a custom-built one that manages all of that for us. But OK, next step. Concurrency is going to be a new concept to your engineers. So remember, when we were building applications on EC2, the scaling mechanism, the thing that drives scale on any EC2-based environment is TPS, right, or RPS, requests per second. The more you have, the more you have to scale out, or the more memory you have to add, horizontal or vertical scaling. Working in Lambda is a little bit different, right? That's no longer really the limit. The thing that we care about is concurrency. And what concurrency means is the number of in-flight Lambda functions that are operating at any given time, processing requests. By default, our accounts anybody creating a new account starts at 1,000 concurrency. You can create a support case and lift that up to, I've seen people with like 30, 40,000 concurrency. So you can run like an enormous amount of Lambda functions at any given time. But the side effect of what happens with that is when you're not running any Lambda functions, AWS has to warm them up when the first invoke request lands on your service. So that, as you can imagine, warming up a container that runs your function takes a little bit of time. And that's called a cold start. So a cold start is downloading your code that's stored in S3, loading it onto an execution environment that AWS does for you, and then beginning execution of that handler that we just saw. So that's called initialization, right? So in your logs, you'll see that. You'll see an initialization. Now, once your functions are warm, the next invoke that lands is going to be really quick, like 10, 20 times faster. And that's called a warm start. So concurrency is always measured by this formula here, right? It's average request per second. Everything is measured in seconds. So average TPS driven to Lambda times the average request in duration for Lambda. So let's imagine 3 examples. You have RPS starting at 100. They're all starting at 100. Right? And we'll see how this affects concurrency. First example, RPS starts at 100. It runs your functions average for 500 milliseconds. So that's half a second. That means your concurrency needs actually go down as compared to your requests that are coming in. It's going to be 50 concurrency. Now let's say the same example, 100 RPS, running for an average of 1 second. That means your concurrency needs are exactly 100. And then last example, if your durations start going above a second, so we're at 2 seconds, that's just 100 times 2. So now you're going to need 200 concurrency in your accounts to service this use case. So if you're working in Lambda, ideally, we want to drive the invocation times down, like below 1 second to optimize for concurrency. Right? So this model, the scaling mechanism at which AWS will allow this to scale up, I believe just changed like yesterday. Right? It used to be you could burst to 3,000 and then increase by 500 concurrency every minute. I think it's just now you can increase by 1,000 every 10 seconds. Right? So just keep that in mind. There's like a 12x increase in how AWS will allow us to scale our functions out. OK, so one thing we learned is you have to set development standards. And one thing that we set was, so you can create an alias that is basically a pointer that points at any Lambda function, or even multiple versions of the same function. We've standardized and created a single alias for all Lambdas, and that's called live traffic, live_traffic. And the reason we do that is because if I need to support a dev team, and I work with hundreds of them on a daily basis, right, always questions coming in, I can go to any application team, and I know exactly where the entry point for that Lambda function is going to begin. It's always live traffic. Right? Behind the scenes, it could be anything, but I know exactly where these functions begin. And if I'm an engineer who gets loaned out to a different team, I also know like how this Lambda function will begin. You don't have to do this, but it's obviously not a requirement. It's just a best practice we thought works well for us. And then we take advantage of Lambda function versions. So by default, all Lambda functions have this like latest, $latest like name. You really don't want to use that because anybody can go into your environment and change latest. And it can always be changing. So essentially, you can have production Lambda functions that could change if you make a mistake. So what AWS does is you can create new versions on top of latest. And those are pinned and immutable. Right? So you'll have safe Lambda functions. And if you want to create a new version, you go through the versioning process. And then for us, we always encrypt environment variables. Right? We don't know what's in them, right? Like you could put secrets in them, you could put nothing in them, but it's always a safe practice to encrypt them. AWS gives you the features to do it. You can use KMS, either a CMK, a customer managed key, or just an AWS managed key. And then we also standardize tags, right? Tagging is like one of the ways to put metadata on any AWS resource. And so standard tags help us with everything from who to contact if the service has a problem, but also like how do we bill application teams for their AWS consumption. So we might have 10 app teams that are in one account. And how do we triage that billing? So like we have owner contact as an example. We have the application name, and then who created this, what tool created this resource. So one pipeline is the name of our CI/CD pipeline. So when we automate deployments, everything is tagged with a one pipeline signature. Right? So we know that our tooling created it. If this tag is missing, we know that it was created manually, and we have a tool that actively looks for non-compliant resources. And then IAM policies are the most important. Right? IAM controls what my Lambda functions can do and basically what kind of access you have in your application code. Right? It doesn't matter if your code tries to write to Dynamo, SQS, create EC2 instances. If it doesn't have access in the Lambda execution role, you're not going to be able to do that. And the goal here is to limit access in the policies that you're writing. Right? We don't want to have a ton of wildcards. We use a tool that all developers go through to create IAM policies, and it's looking for really wide IAM policies. Another example is you have trust policies in all of your Lambda roles. Who can assume your role, essentially? You don't want to have too many principals that can assume the same role. Like we usually only allow a single trust in a single trust policy. Right? That way you know exactly who is capable of taking over this role. And then just enforce standards. Like start early and make sure standards are being enforced. I think many of you may have heard of a tool called Cloud Custodian. Capital One open sourced this tool, and it's basically an auditing tool that runs in your accounts, and it looks for all of these policies. You can write your own policies, but if I deploy a function that is not compliant, I get an email within like 5 minutes saying this is X, Y, and Z is not compliant, and then in an hour it goes and deletes my function. So if I don't address it, right? So we use AWS orgs. So remember, we create thousands of accounts, and we don't want those accounts to have different configurations, different permissioning. So we use orgs, and we use org SCPs to block things that we don't allow. So a Lambda feature, does anybody use like Lambda function URLs? The service team will call them like FURLs, but essentially it's like you can open up a Lambda function and put an HTTP endpoint on your function, right? And I think that's it. Like cost-wise, that's awesome. Like I can invoke a function through an HTTP endpoint, and it's all free. The problem is they're all public, and we don't allow anything to be public at Capital One, except for obviously our things that service our website. But so we have an SCP that blocks that feature. Like nobody can use it. So you can be very prescriptive on what's allowed and what's not through an SCP. And then early on, we learned that you should vend multiple accounts to the same dev team or the same group of application owners. And the reason you want to do that is you want to vend like different tiers of accounts, so dev, QA, and also performance testing before production. That way you can deploy through different mechanisms and have stricter and stricter rules in every account. Right? And we use orgs to do that as well, to create all this stuff. So for the most part, most app teams end up with 3 to 4 accounts per thing they're trying to build. And that's why we have a lot of accounts. Early on in our days, we used gigantic big accounts. And I think that's common for most people who are getting into AWS. Right? It's easy to manage one big account. Right? You don't have like us, we have tons of accounts. But when you need to get out of that, everybody in that account shares the same limits, the same scaling mechanisms, and it's really tough to blast radius. So we want to manage small accounts and vend these to your users. Next thing is don't reinvent the wheel. AWS has created a ton of libraries. Specifically, a really good one is called Power Tools. Most of us are doing very similar things. We're logging, we're creating custom metrics, these are all created for us. Right? Just go to the Power Tools library, download them, and just have your engineers use these. This will also help you standardize how your logs are created and how you trace your applications. And then last thing is at Capital One, we've been driving this mentality that everybody is responsible for cost. Right? As a serverless developer, you no longer have an infrastructure team who is managing that cost. Right? I'm the developer, and I'm responsible for this Lambda function and everything it cost me. So make sure you know the Lambda pricing formula. Right? The pricing formula for Lambda is memory configured times how long it ran for. So we just saw in that SAM demo, this is what every single Lambda log looks like, start, end, and then the report line. The report line is the most important. You'll have these fields on every single report line, and you'll be able to identify exactly how your function performed. And this is an example of that. So at the very bottom is the report line. We can see this function ran for 7.3 milliseconds. And then the memory used, so this is where it's going to be different from your local SAM, was 91 megs. And it was configured at 256 megs. So in theory, this function could be reduced in size to save me money. And then the very right there, init duration, is the cold start. It took me 800 some seconds to initialize this function. And that's basically a performance penalty before your function you can even begin execution. So at Capital One, we deploy a tool called Lambda Power Tuner across the enterprise. And what Lambda Power Tuner allows us to do is it automates the testing, the performance testing of your Lambda functions and helps you with identifying the right memory setting for your function. So if you notice, like, there's no way for you to configure CPU settings in Lambda. Right? The only setting you can configure is memory. And what AWS does is, as you increase or decrease memory, they give you a proportional change in CPU power. So the side effect is you can run faster, maybe, if you have more memory. So if you have like a CPU-bound workload, you may want to use more memory than you actually need to run faster and get that work done quicker. So remember, the pricing formula is two pieces, right? It's memory configured times execution duration. So it's kind of like there's no science to this. Like every function needs to be performance tested, and that's what you're seeing here. So the Power Tuner will give you a graph. The red line represents invocation time, and that's basically performance. The lower the better, right? And then blue line represents cost. Also lower the better, right? But so as we move across the right on the x-axis, we start at 128 megs of memory and move all the way to 4 gigs of memory. And as you can see, all the way on the left, at 128, my performance was pretty bad, right? And as I increase memory, performance gets better and better. And that's because I got more CPU power for this workload. Now, at some point, these lines cross. And then actually, as I increase past about a gig of memory, that's where the crossover line is, it doesn't really help me anymore to add more memory. In fact, it costs me an astronomical amount of money to do that. And that's because every workload has like a CPU profile, and as you know, adding more CPU doesn't always, at some point, has a diminishing return. Right? So like this workload belongs somewhere between 512 and a gig of memory. And that's just something you have to work through with your dev teams. And imagine, if I set this function to 4 gigs, you have a ton of waste with this function. And if you have 100 functions doing this, that's tons of value that you could be getting back. All right, last section here, we have 10 minutes. So I wanted to leave you with a list of best practices and things to do and probably you want to avoid based on experience. So first thing up is things not to do. And feel free to take pictures of this list, but I won't go through every single one of these lists, but number one is like really important. So Lambda functions can be set to have 15-minute execution timeouts or and up to 10 gigs of memory. You generally don't want to do this. Right? If you're running into dev teams that are setting maxed out configs, they probably need to think about re-architecting their workload so they don't need this kind of configuration. So the reason is, for example, if you were to set a 15-minute timeout, but you believe your average duration for this function should be like 1 minute, your functions, if there's any kind of problem within your function, and what happens a lot is network timeout, it will just time out all the way up to 15 minutes, and then you just pay the max value that you would ever pay for this function. Right? And I've seen this happen many, many times. So just be careful. You should probably set your functions to, values should be within 20 or 30% of what you think the performance should actually be. And then also, setting your functions at the bottom, you default to 128 megs of memory, is generally not good for production performance. So remember we said memory controls CPU. So at 128 megs of memory, you're getting almost no CPU. So you'll notice on almost every use case, when you go from 128 to 256, it's going to be an awesome performance improvement, and it's something you probably want to do. Right? Number 2 is cool. So if you're writing, so like by default, I think there's 7 or 8 metrics that AWS will create for you. You can go to the console and you can look at those metrics for Lambda. But most of us need better metrics, like things that actually matter to our application. So there's 2 ways to do that. One way is to use the put metric API for CloudWatch to create metric data. And that call is, the API call is really expensive, right? So try to avoid that call. It's one of the most expensive API calls I've come across, right? So avoid that call. Instead, use something called EMF. So EMF is the embedded metric format. You just write a JSON like log template in your CloudWatch logs, and AWS will pick that up and then create a log asynchronously, or create a metric asynchronously. Right? The rest of these, just make sure you're not doing, make sure you're using the right CPU architecture. So Lambda can run on ARM, and it can also run on x86. Generally, x86 will perform worse than ARM in most use cases. So ARM is going to be better for the majority of our workloads. There are some exceptions. You want to test this, and it's really easy to do. Just take a function and change the architecture. But generally, if you have really big functions, lots of memory, x86 it may perform better. But in most of the use cases that we've seen, ARM is cheaper. It's about 20% cheaper than x86, and it runs better. So give it a shot. And then, all right, so these are just the best practices that we use all the time at Capital One. Number 1, we talked a lot about this, optimize everything, right? Optimize performance, tune your application. And obviously, this depends on your use case. You may have a use case that says, I want the best performance no matter what. I don't care about cost, right? Or you have another use case that I want to blend. So it's definitely something your developers have to think through. CloudWatch logs are not free. They cost you 50 cents, I think it's like 53 cents per gigabyte. And by default, they retain forever, right? So I've seen use cases where the logging cost for your application is more than the compute cost. And that's definitely something that you don't want anywhere to happen ever, right? So make sure you're setting CloudWatch log retention policies. You set it in days. So, and you want to be very aggressive in the lower level environments. Like development, you don't want your logs sticking around for 365 days. Like that doesn't serve any purpose, right? I think at a recent launch, about a week ago, you can now set CloudWatch log infrequent access. So if you have logs that don't need to be accessed often, you can even tier your logs. Use Lambda Power Tools, right, for your common tasks. For those, is anybody using provision concurrency with your Lambda functions, PC? So PC is a really cool feature. What it does is, remember the cold and warm cycle that Lambda functions go through? Now, you may have a workload that doesn't have that traffic pattern. It's always warm, always doing stuff. So you can set PC on it in order to keep those functions warm at all times, right? And the trade-off is that it costs you money whether you use the function or not, right? So make sure you're setting auto-scaling on your PC if you are using it. Right? Every PC setting should be auto-scaled. Like for us, a lot of our workload is follow the sun. Right? Customers wake up, they do work, it stays high, traffic stays high, then it ramps down as the West Coast hours start ramping down. And then we talked about SAM. Use SAM to improve your iteration and development speed. And then number 8 is really important. So AWS offers SDKs for every language, but they have multiple major versions of these SDKs. The older the number, right, version 1, 2, those are SDKs that are generally designed before Lambda even existed. So those are really big SDKs, and they're not modular. So you want to use the right SDK version. For example, in Node, right? Version 3 is designed to be modular and help your Lambda performance. So don't use version 2, use version 3 if you're using Node. Same example exists for other runtimes. And then number 9 is really cool. It's a feature called Snap Start. You know, many of us have Lambda functions written in Java. And Java is known for having really bad cold start timings. And that's just because the JDK, the JVM is slow, right? It just takes time to boot up no matter where you are. So the Snap Start, what it does is AWS snapshots your Lambda function profile, and it warms it up, and it uses a warm snapshot to invoke your function. So it can drastically reduce cold start timing. We've seen from our testing 90+%. So you can go from like 15 seconds of cold start down to like 1 second. And it's the best part is it's free. Like AWS doesn't charge us for any of this stuff, right? And then the last thing, standards, right? You don't have to use the standards that we set, but just set standards that work for your organization and discuss that, and then agree on that across your entire set of stakeholders. So that's basically all we have to cover for today. I encourage you to put in your session feedback in the survey. And thanks for your time. And I'll be sticking around if you have any questions. Thank you.